Imagine standing in a dimly lit 17th century laboratory. A physicist takes a long glass tube, fills it to the brim with liquid mercury, a remarkably heavy, dense metal, and flips it upside down into a shallow bowl. Gravity should immediately pull all that heavy liquid out of the tube and into the bowl. But it doesn't. A massive column of mercury simply hangs there, suspended. What invisible force is holding up? To solve this, we have to rethink our entire environment. We walk around every day feeling mostly weightless, but we actually reside at the very bottom of a deep, heavy ocean of air. This atmosphere stacks for roughly 100 kilometers above our heads. It has mass, and gravity pulls it down. This exerts a massive, constant baseline force on everything it touches. In 1643, Evangelista Torricelli realized that the weight of the sky could be calculated by balancing it against a column of heavy fluid. This mercury barometer functions as a specialized scale designed to weigh the Earth's atmosphere. The mechanics are straightforward. The weight of all that overhead air continuously pushes down on the exposed mercury in the shallow bowl. That downward pressure physically forces the liquid up into the glass tube until the two competing forces balance. The floating column of metal from our 17th century lab is not an anomaly. It is locked in a perfect tug-of-war with the weight of the Earth's atmosphere. This diagram strips the barometer down to its underlying mechanics to show the exact mathematics driving this balance. Look at the very top of the glass tube. This space is a vacuum. Because there is no air inside to exert force, it pushes down with zero pressure on the fluid below it. On the outside of the tube, at point C, the full weight of the atmosphere is pressing down on the open liquid surface. In a continuous fluid at rest, the pressure is exactly the same at any given horizontal level. This means the pressure at point B, inside the tube, is identical to the atmospheric pressure outside. This gives us our formula. Atmospheric pressure is equal to the fluid's density, multiplied by gravity, multiplied by the height of the column. By simply measuring the height of a trapped column of liquid with a ruler, physicists can calculate the exact weight of the sky above them. Shifting to the deep ocean demonstrates how these pressures compound. The total pressure acting on a submarine's hull is the crushing weight of the ocean water plus the entire weight of the atmosphere resting on the ocean's surface. This inescapable combined total weight is defined as absolute pressure. Absolute pressure is the total force pressing down on an object from all the fluids stacked above it. Measuring pressure inside a closed system, like a gas line or a bicycle tire, requires a different approach that ignores the weight of the atmosphere. This is the open tube manometer. One side attaches to a closed system, the other opens to the room. Pressurized gas pushes down one side, the atmosphere pushes back, shifting the fluid. This height difference represents gauge pressure, internal pressure minus atmospheric pressure. A manometer isolates the stress inside a closed system, ignoring the total weight of the environment. These two instruments measure two distinct aspects of fluid mechanics. The barometer measures absolute pressure, the unavoidable baseline weight of our environment. The manometer measures gauge pressure, the localized difference inside a specific container. If absolute atmospheric pressure is the invisible floor we all stand on, gauge pressure is simply the step up from that floor.